All right, this is Trig section 7.4. Today we are looking again at vectors and something called a dot product. So this is kind of like the other stuff we did with vectors. It was pretty simple. So like the stuff you did in 7.3, it was terminal minus initial, some pretty simple math stuff. To find a dot product, it's also simple math stuff. You just have to know what it is you're supposed to do as you're doing it. So it's another problem or another lesson that's important that you actually go through and do some practice on these things. All right, so first off, to define here dot product, if you have a vector u, which is u1, u2, and a vector v, v1 and v2, the dot product of u and v, or you just say u dot v, and it is a dot kind of like the little multiplication symbol that you've seen in the past. The way that you find this is we are going to take u1 times v1, so you multiply the x components, then you're going to add to it u2 times v2, so you're going to multiply your y components. So whenever you do this, then the dot product of two vectors is always going to be a scalar, which remember from previous lessons, all a scalar is just a number. So a dot product is always going to equal a number. You're not going to get a vector back out of it. It's just a single number answer. Some properties for these dot products. If we have vectors u, v, and w, and c as a scalar, our first property is u dot v is the same as v dot u. So it doesn't matter the order that they give it to, you're going to end up with the same dot product either way. The next one is if you take the zero vector, so remember that's your bold 0, which would be like the vector 0, 0, and you multiply it by a vector v, you're going to get the number 0. So you want to make sure that whenever you're taking your notes here, make sure that this one is bold, or give yourself a note here that that is a vector and this 0 is a number. The third property is that if I take u dotted with the sum of the vectors v and w, so v plus w and then dotted with u, that is the same as taking u dot v plus u dot w. So you can kind of think of this dot product as being distributive. The fourth one is if you take a vector and you dot it with itself, you're going to end up with whatever the magnitude of the vector is squared. And then the last one is if you have a scalar c times the dot product of u and v, you can take that scalar times the first vector u and then dot it with v, or you can take u and dot it with the scalar c times the vector v. As long as everything gets multiplied together, it all works out to the same thing. Now, the only thing that in these is the one that you really got to kind of pay attention to is number 4. This is going to be something that this property is useful to know. And we'll run across, I'm pretty sure in today's lesson, an example that uses that idea that will help us to, solve the problem. All right, so first we're just going to practice finding these dot products. So here, if we're dotting these two vectors together, remember you have to multiply the x components, so 4 times 2, and then you add to it the y components multiplied, so 5 times 3. 4 times 2 is 8, 5 times 3 is 15, and 8 and 15 is 23. So the dot product of those two vectors is just simply a 23. On the next one, part B, multiply your x's, so 0 times 4, plus multiply your y's, 3 times a negative 2. 0 times 4 is 0. 3 times a negative 2 is a negative 6, and 0 minus 6 is a negative 6. So the dot product of those two vectors is going to give you a negative 6. Example 2. Here we're going to do more dot products. They define these vectors u, v, and w for us. For this first one, they want us to find u dot v and then times w. Now, this isn't one that we had up in the properties up above, but I want you to stop and think about what kind of an answer we're going to have for a problem like this. because whenever we take this u dot v, which order of operations says to do the parenthesis part first, we just said that anytime you take the dot product of two vectors, you're going to get a number or a scalar. Then we're going to take a scalar times another vector, just like you did in the last lesson, which is going to produce a vector. So this is going to end up equaling another vector answer. So for this one, first we need to find what u dot v is. So u dot v, we need to multiply the x components, so -1 times 2, plus the y components, 3 times the -4, which is going to be a -2 minus a 12, which is a -14. Then it's this -14 that we are going to multiply by that vector w, which is the vector 1, -2. And then remember here, when you multiply a scalar times a vector, it's just kind of like multiplying and distributing. So we're going to get a -14 for the x component, and then a +28 for the y. And there's our final vector answer. Now for part B, we're going to take this 2 times that vector v, which is going to give me another vector. Then I'm going to take a vector u dotted with a new vector, and a vector dotted with a vector is going to be a scalar. So this one's going to just equal a number. So first I'm going to figure out, well actually I can just write it out here. My u is the -1, 3. I'm going to dot that with 2v. So if I multiply 2 times v, it's going to become 4 and then a -8. So those are the two vectors I'm finding the dot product of. If I multiply the x's, I get a -1 times a 4. Add to it the product of the y components, 3 times a -8. That gives me a -4. That gives me a -24. And -4 minus 24 is going to give me a scalar value of -28. So you just want to be careful that you're getting the right kind of answer out of these problems, meaning you want to check to see, is it supposed to produce another vector, or are you going to end up with a scalar when you do all of the math? All right, example 3. The dot product of u and itself is 5. So this first part here is telling us that u dot u is 5. We're supposed to find the magnitude of u. This is where we're going to use that property that we had up above, number 4, that I said the only one you really need to kind of stick in your memory bank here, is that a vector dotted with itself is its magnitude squared. So this vector u dotted with itself u is its magnitude squared. Well, I know that it equals 5, so that tells me that the magnitude squared is 5, and if I want to solve for the magnitude of u, I would have to square root both sides to get rid of the square, so the magnitude of u is just the square root of 5. All right, flip on over to the back side. Here we are going to look at finding an angle that is between two vectors. So in the last lesson, you were able to find the angle that a vector made with the positive x-axis going counterclockwise. What we're going to look at today is an angle that happens in between two vectors. So say you had a vector u here, and we had a vector v that sat here. When we're talking about the angle that's between, the theta that we're looking for is the angle here that's between the two vectors. Now, in order to find that, we're going to have a formula here that says cosine of theta equals u dot v. So you're going to find the dot product of the vectors divided by the magnitude of u times the magnitude of v. So again, though, just like whenever we were doing the stuff with the tangent and that formula in the last lesson, to actually find this angle, you're going to have to take the inverse cosine of whatever you get whenever you number crunch this stuff here. We also do want to double check to make sure that our angle that we're getting actually makes sense with a picture. So just like we did before on problems like these, you're going to want to actually go out and kind of draw these off to the side to give yourself a visual of what's going on to help you to kind of see what that angle should be. So if I start with u, U is the vector 4, 3. Let me go ahead and mark. I'm just going to mark the x and the y up to 5. So 4, 3 is 4 on the x, 3 on the y. So there is my vector u. I won't label the u because I'm not sure where to put it because the other line's got to get drawn in. We'll label here in a sec. And then v is 3, 5. So 3, 5 would put me up here. So this was u, this is v, and we're looking for the angle between them. So first thing I need in order to use this formula is I'm going to need to know what is u dot v. So u dot v, remember we multiply the x's, so 4 times 3. Add to it when you multiply the y components, 3 times 5. That would be a 12 plus a 15, which is 27. Then I need to find the magnitudes. So we'll start with the magnitude of u, which now remember to find magnitude, it's the square root. You have to square the x component, square the y component, add them together. So I'm going to go ahead and just write what they are when they're squared. So 4 squared is 16. 3 squared is 9. If I add 16 and 9, I get the square root of 25, which is just a 5. And then the magnitude of v, again, it's square root. You square the x to get a 9, square the 5 to get a 25. 9 and 25 makes the square root of 34, and the square root of 34 actually will not break down, so it stays just the square root of 34. So now we have all the pieces that we need to write out this cosine theta formula. Let's go ahead and fill in the parts. So we know that cosine of theta is u dot v, which we said was 27, over the magnitude of u times the magnitude of v. So this 5 times that square root 34, so just 5 square root 34. And now in order to find that theta value, we're going to have to take the inverse cosine of this fraction. So inverse cosine of 27 divided by, if you're punching it in like this and not putting it in as a stacked fraction, be sure that you're putting in parentheses everything in the denominator so it knows to divide by both the 5 and the square root of 34. Close the parenthesis around that because that shows all the stuff there is in the bottom. Close the parenthesis for my inverse cosine. And I end up with 22.2 degrees. And looking at your picture, 22.2 degrees is a feasible answer because you can see that it sits here in the first quadrant, so definitely it's going to be less than 90 degrees, that angle between. It's a little guy, so this 22.2 does fit. Now, with this formula, we could go through and rewrite this formula so that it looks just a little bit different. What we could do is we could actually take this formula and solve it for the u dot v and say that u dot v equals, and if we did, we would have to multiply those magnitudes over. So it would be the magnitude of u times the magnitude of v times cosine of theta. And we're going to actually use this formula whenever they give us the magnitude of u, the magnitude of v, and a theta, and then they'll be asking us what's the dot product. Now, the reason this is important and helpful is we've got this other thing here that is something called orthogonal. So two vectors u and v are orthogonal, which what orthogonal means is perpendicular. And if you remember back from geometry, that's the symbol for perpendicular. So two vectors are going to be perpendicular to each other. There's the lights. If the dot product of u and v is 0. So if they give us the vectors u and v and we can find the dot product and show that they're 0, we can see that they're orthogonal. Or if they give us the magnitudes and the angle, actually if they give us the angle between, we'll know they're orthogonal because it'll be a 90-degree angle. So this here, rewriting it like this, that's something that is kind of like a particular for different kinds of situations that you come across, different problems. You're going to mainly be looking for the angle between and not necessarily be given the angle between. But just know that that is there, that you can rewrite the formula that way. All right, so for example 5, we're going to answer whether or not these guys are orthogonal. So in order to test it, we have to find the dot product. And we are just testing to see, does the dot product equal 0 or not? So x times x is 2 times 6, plus y times y is negative 3 times 4. 2 times 6 is 12. Negative 3 times 4 is a negative 12. Those make 0, which means then that yes, those two vectors actually are orthogonal or perpendicular. All right, now the last stuff that we're going to get into is going to feel a little bit more physics. So for this first part here, picture this to be, and if you look in your boat, in your book, it's a boat that's on a trailer that's going up a ramp. You can think of it as anything that's on a wheel getting pulled up a ramp. So this is our ramp here, and what's happening is that we have this force here that's pulling the boat because of gravity, and this F force is made up of your W2, which represents the force that's going against the ramp, and this W1 is the force that is pulling the boat down the ramp. This overall force here is made up by these two components here, W1 plus W2. Because if you look here, and if you were to take this vector and add it to the other, so we're picking it up, putting it on the end, it's going to end up down here creating that force straight down. So what we could think of then is that the negative component of this W1, so going up this direction here, that represents the force that you would need to keep the boat from rolling down the ramp. And the W2 force represents the force that the tires must withstand against the ramp. Now, we're not going to be doing so much force component stuff like that. We're actually going to do more problems a bit more like this second part over here. And what this is, which is kind of, involved with what we were doing here, but we're going to word it more like what we have in example 5 and not so much word problems with force and work and things like that. So if we have these vectors here, I have a vector v and a vector u. Here I can see I've got a vector w and then a vector w1, which runs along v here. This w1 vector is said to be the projection of u onto v. Now, the way that you can think of that, and the way I've always described it in the past to students, is by projection. Picture that if you had some kind of light that was up here, and that light was shining down on on u, it's going to create a shadow that comes down on V and creates this W1. That's what that projection is. It's if you held a light that was perpendicular to the vector that you're projecting onto, it's the shadow that it would make on it. The way that we write it is we say that this W1 equals PROJ for projection, a little v because we're going onto v, and then a u because we're projecting u. So that's the projection of u onto v. And then this vector u is actually made up of the vector w1 plus this w2. Because if I took w2 and I moved it over and added it on to w1, those two summed together would create this point, which is my vector u. So this is w1 plus W2. You do need to know that W1 plus W2 is U. We'll be using that in some of our problems, but the big thing here that we need to know is this formula for the projection of U onto V. So there's that notation again, projection of U onto V. What it is it is U dot V over the magnitude of v squared times the vector v. So magnitude is a scalar. If you square it, it's still a scalar. U dot v is a scalar. A scalar divided by a scalar is still a scalar. And then when you take this scalar times that vector v, we're going to get a vector. That vector that we get, remember, is then our W1. So what this does then is it gives us the formula and tells us what that vector there is actually going to be. If we held the light, shine the shadow perpendicular to V, and found what that vector would be of that shadow. So for the last example 5, it is set up just like I said here with the idea of calling it a projection. We're going to find the projection of U, which is 3, -5, onto V, which is 6, 2, and the vector component of U orthogonal to V. What that is talking about, the vector component of U orthogonal to V, what that is asking us to find is that is asking what is our W2 vector. So they're not going to just straight up in these problems say what does W2 equal, but you have to know from here on out in the future on tests, things like that, that anytime that says and the vector component of U orthogonal to V, they're looking for W2. With this, when we go to find it, remember that U was made up of W1 plus W2. So we'll come back to that here in a second. First, let's find the projection of U onto V. So that's this formula here. In order to find it, first we need to know what U dot V is. So U dot V is 3 times 6 plus our Y is -5 times 2. 3 times 6 is 18, -5 times 2 is -10, and 18 minus 10 is 8. Then we need to know what the magnitude of V is, which is the square root. Remember, we square the x component, square the y component, add them together, and square root the whole thing. So 6 squared is 36, plus 2 squared, which is 4, which would be the square root of 40. But then remember, don't break this down, because we then actually need to take that magnitude of V and square it, because that's what we use in the formula, is that thing squared. So if I square the square root of 40, I'm just going to get a 40. So my U dot V over the magnitude of V squared is actually going to be 8 over 40. 8 over 40, we can actually get to reduce. They both will divide by 8, so that's really going to be 1/5. So my projection of U onto V, so U and little v, it's going to be that 8 over 40, or 1/5, times the vector V, which is 6, 2, which if we distribute, we are going to get the vector 6/5, 2/5. That is the projection of U onto V, which is the same as W1. Now on to the second part of the problem, where they wanted us to find the vector component of U orthogonal to V. Here's where we're going to go back to the idea that U was composed of two vectors, W1 plus a W2. So if I use this to set up an equation with my vectors, that means that if I want to figure out what W2 is, I would have to subtract W1 from U. So that's exactly what we're going to do. We're going to take our vector U minus our vector W1, which we just found. So U is 3, -5. And from that, I'm going to subtract this vector W1, 6/5, 2/5. So if we go through and we do some common denominator stuff to find our, let's see, I'm going to go ahead and label it W2 equals. To find our x component, we're taking 3, subtracting that 6/5, which is going to end up at 9/5. And then for our new y component, we need to take the -5, minus the 2/5, which when we common denominator is going to end up giving us a negative 27/5. So that is the vector component of u orthogonal to v. So the work to do these isn't hard to do. You just have to understand what it is that you're looking for, what it is you have to work through and get as you're going through these problems. So like I said, you have to know when it says the vector component of u orthogonal to v, that means find W2, and you need to know that u is just W1 plus W2. All right, you guys are on page 580, kind of like before. It looks like there's a lot of problems, but really it's not too terribly bad, simply because a lot of the problems are going to be pretty quick that you go through.